At the end of 2023, the sun produced its strongest solar flare of the year. Less than 24 hours later, a powerful magnitude 7.5 earthquake struck Japan's Noto Peninsula. A recent study has suggested that this timing may not be purely coincidental, proposing that disturbances in Earth's ionosphere caused by intense solar activity could slightly influence when a critically stressed fault finally ruptures. The idea is controversial and far from proven, but it has sparked serious scientific discussion. In this video, we will examine what the study claims, what experts say, and what it really means. Let's get started. The study behind this discussion was published in the International Journal of Plasma Environmental Science and Technology by researchers in Japan. It does not argue that solar flares create tectonic stress or directly generate earthquakes. Instead, it explores whether intense solar activity might influence the precise timing of rupture when a fault is already very close to failure. The sequence that drew attention began on December 31st, 2023, when an X-class solar flare erupted from the sun. X-class flares are the most energetic category of solar flare, capable of disturbing Earth's magnetosphere and significantly altering the ionosphere, the layer of charged particles in the upper atmosphere. Space weather instruments recorded increased ionization and geomagnetic fluctuations following the event. On January 1st, 2024, a magnitude 7.5 earthquake struck the Noto Peninsula in Japan. The quake caused extensive damage, hundreds of deaths, and widespread infrastructure disruption. Japan is one of the most seismically active regions on Earth, so large earthquakes are not rare. What made this case notable was the short interval between the flare and the earthquake. The researchers proposed a physical framework to examine whether this alignment might represent more than coincidence. Their model treats Earth's ionosphere and crust as parts of a coupled electrical system. Solar flares increase electron density in the ionosphere. According to the study, strong disturbances can push charged particles downward, altering the electric field between the upper atmosphere and Earth's surface. Fault zones deep within the crust are mechanically complex and often fluid-filled. Fractured rock systems can respond to electrical forces in subtle ways. In the model described by the authors, some fault regions may behave similarly to capacitors in an electrical circuit, capable of storing and redistributing charge. If ionospheric conditions shift rapidly due to a powerful solar flare, the resulting electrostatic imbalance could slightly modify stress conditions along a fault. Under normal circumstances, these forces are extremely small compared to tectonic stresses generated by plate motion. However, if a fault is already critically stressed, meaning it is near the threshold of rupture, even a small perturbation might influence the exact moment when slipping begins. The authors also referenced a December 2025 earthquake that followed another strong solar flare, suggesting that similar temporal alignments may warrant investigation. At this stage, however, these examples serve as prompts for further analysis rather than evidence of a proven pattern. The significance of this hypothesis lies less in its immediate conclusions and more in its interdisciplinary scope. Earthquake science traditionally focuses on plate tectonics, stress accumulation, frictional resistance along faults, and long-term geological processes. Space weather research, by contrast, focuses on plasma physics, solar radiation, geomagnetic storms, and ionospheric dynamics. Bringing these domains together introduces a broader systems perspective. Earth is not an isolated mechanical structure. It is embedded in a dynamic space environment shaped by solar activity. The question is whether that environment exerts any measurable influence on deep crustal processes. This idea intersects with a field sometimes referred to as seismoelectromagnetics. Researchers in that area have investigated whether electromagnetic anomalies might precede earthquakes, or whether electrical properties of rocks play a role in rupture dynamics. Although intriguing observations have been reported in the past, no consistent predictive electromagnetic signal has been established. The new study shifts focus from electromagnetic signals produced by earthquakes to the possibility of electromagnetic disturbances acting as external triggers under very specific conditions. It does not replace tectonic theory, but proposes a potential interaction at the margins of instability. Skepticism remains strong within the geophysical community. One major concern is statistical interpretation. Solar flares occur frequently, particularly during periods of high solar activity. Earthquakes also occur frequently around the globe. Given the number of events in both categories, some close temporal alignments are statistically inevitable. Without large-scale analysis across many years of data, individual examples cannot establish a meaningful relationship. Another concern involves physical realism. Earth's crust is electrically heterogeneous. Rock layers differ widely in conductivity and resistivity, and deep crustal formations often have substantial electrical resistance. These properties could significantly dampen or block the transmission of ionospheric electric disturbances to seismogenic depths. Moreover, tectonic stress accumulation involves immense mechanical forces generated by plate motion over decades or centuries. The energy released during a major earthquake far exceeds the scale of electrostatic forces described in the model. Any external electrical effect would operate within this overwhelmingly dominant tectonic framework. The researchers acknowledge these limitations. Their proposal is framed as a hypothesis within complex system science, where systems near critical thresholds may be sensitive to small perturbations. Whether such sensitivity applies to earthquake initiation remains an open question. If future research were to identify a statistically measurable relationship between certain solar flares and the timing of major earthquakes, the implications would be nuanced rather than transformative. Tectonic processes would remain the fundamental driver of seismic activity. However, seismic hazard modeling might consider whether space weather conditions modestly influence rupture timing in rare, critically stressed scenarios. Testing this possibility requires extensive data. Researchers would need to analyze multiple solar cycles and thousands of seismic events, examining whether large earthquakes occur at a higher than expected rate within defined time windows following intense solar flares. This would involve careful statistical modeling to separate genuine patterns from random overlap. Interdisciplinary collaboration would be essential. Space weather monitoring systems already track solar flares, geomagnetic storms, and ionospheric electron density using satellites and ground-based observatories. Seismic networks provide high-resolution data on fault activity worldwide. Integrating these datasets over long time spans could clarify whether any consistent signal exists. If no measurable correlation emerges, the hypothesis will likely be set aside. That outcome would still contribute to scientific understanding by refining the limits of ionosphere crust interaction. Eliminating weak mechanisms is part of strengthening theoretical frameworks. It is important to recognize that this line of research does not offer a practical earthquake prediction method. Even if a subtle modulation effect were identified, determining which faults are critically stressed remains one of the central challenges in seismology. Predictive capability depends primarily on understanding stress accumulation, fault geometry, and historical rupture patterns. What this discussion ultimately reflects is the complexity of Earth as a coupled system. The Sun undeniably influences Earth's magnetosphere and upper atmosphere. Whether that influence extends in any measurable way to crustal rupture, timing is a question that can only be answered through rigorous analysis. The researchers involved have indicated plans for broader statistical evaluation. Only through long-term quantitative study can this hypothesis be confirmed or rejected with confidence. The idea that solar flares might influence earthquake timing is intriguing, but still unproven. Tectonic stress remains the dominant driver of seismic events, and strong statistical evidence is still needed. Only deeper analysis will determine whether this is coincidence or a subtle interaction worth redefining.